Thanks, mate. Can everybody hear me okay? Yes. Good. Excellent. Good. Great. So my name is Mitch Beaumont. I work for AWS. I'm part of the solutions architecture team, and I'm based here in Sydney. I had the pleasure of talking at Container Camp last year down in Melbourne, and I talked about one of our open source projects we were working on, which was the containerd. Sorry, is that coming up okay? There we go. Which was the VPC CNI plugin, and that was a CNI plugin that we'd written to help integrate Kubernetes more natively with VPC. That's come a long way since I presented last year, and I'd encourage you to take a look at that project now. I think we're pushing towards version 2, so there's some interesting enhancements there. But I thought I'd go one step better today and talk to you about two open source projects that we've been working on since the last time I came to Container Camp. They are Firecracker and a project which has spun off of Firecracker called firecracker-containerd. But let's start with some basics. Can I just have a show of hands? Who here is using containers in production? Okay, more than I thought. That's good. Excellent. All right, so some of this might seem like 101 stuff to you, but I do want to make sure that everyone's on a level playing field. So what is a container? Well, I mean, simply put, it's a mechanism for deploying and or running software. It allows us to encapsulate a piece of software and all of its associated dependencies. It includes benefits in the realms of isolation and repeatability. And by encapsulating these pieces of software and all the dependencies, we address some of the challenges that are associated with dependency drift and configuration drift as well. They're image-based. Modern containers that we use today through tools like Docker are image-based, and we're able to gain a lot of optimizations, minimal storage, minimal network I/O usage through the use of these layers. And they're very flexible in terms of how we use them. So we can deploy them as a single container, or we can deploy them as multiple containers composed together to make a more complex distributed application. And we've got services born out of that use case, things like Kubernetes, things like Amazon's Elastic Container Service, all designed to help to help solve that problem of managing and orchestrating these composed sets of applications through containers. So how does one go about making a container? Now, the legendary Liz Rice has demoed this at Container Camp a few years ago. She built a container from scratch, so I'm not even going to try and fill her shoes and give you a demonstration of how that actually happens. But I think it's important that we do take a few steps into what is a container. Obviously, for everyone in the room here, it is magic. These things just happen. But there are some fundamental basic concepts that sit under the covers when we deploy a container. So we've got things like namespaces. These are, by the way, these are all Linux primitives. So if we're deploying a standard container on Linux, a Linux-based container, we're using these primitives to construct them. So we're using things like namespaces to give us those visibility controls to isolate what we can see or what the containerized process can actually see and touch, things like file systems and network stacks. We've got control groups which help us limit the types of resources that our process can get access to. So we're talking about CPU, memory, disk I/O. Then we've got a concept called capabilities. These are, again, built into the Linux kernel, and these features allow us to provide more fine-grained access control to containers to restrict the types of calls that our users within those containers can make, as opposed to just saying root or non-root. We can be a little bit more deliberate about that. We've got tools like syscomp, capabilities like syscomp that allow us to limit the scope of the system calls that can be made to the underlying kernel. And then we've got Linux security modules, so things like AppArmor and SE Linux. And then under all of that, I alluded to this earlier on in my previous slide, we have these union file systems that allow us to do things like deduplication of storage and really allow us to optimize the usage of our infrastructure to deliver these containers. So containers versus VMs, it's an age-old battle. What is the difference? And I'm sure everyone has some opinions around this. I thought I'd share a few of mine with you, and hopefully this will help set the scene for the rest of the session today. So the differences are, I mean, if we look at a container to start with, a container, as those of you that are using containers will know, they share a kernel. All of the components, as I've just talked about there, to run a container are actually built into the kernel. This makes containers very quick to start. I boot an operating system, my kernel's already ready, I can start creating containers, and they'll leverage those existing kernel components to run on top of my operating system. Very lightweight, very low overhead, very quick to start. The flip side is obviously virtual machines, and they have a slightly different proposition. They have a more defined isolation boundary, and I'll talk more about that very shortly. The virtual machines, they emulate or they virtualize virtual hardware. In order to use a virtual machine, we have to actually install an operating system. So I need to put a kernel inside of a virtual machine guest to actually run it. Each of those virtual machines is responsible for managing the initialization of that virtual hardware, boot processing, hardware initialization. And then generally speaking, from experience, virtual machines require a little bit more overhead because of these additional capabilities or these additional steps they have to go through to actually initialize themselves. So why would I use a VM over a container? And that is a question that I'm sure many of us spend many nights staring out into the sky trying to ponder and answer that question. I know I do. Well, it all comes down to kernels. I thought that was funny. So if we think about virtual machines have a single kernel per VM. So we have a single, in a standard Linux container, and I'm not excluding Windows, but I'm talking specifically about Linux today. Standard Linux containers have a single Linux kernel per virtual machine. As I said earlier on, a container shares a Linux kernel with other containers running on the same Linux kernel. What this means is that they are sharing the entirety of that Linux kernel interface, and that's quite big. There's a lot going on there. There are a lot of, it can be very hard to reason about the system calls that are being made, the data that's being exchanged and exposed using the proc and the sys file systems on each of those operating systems, which can make it quite challenging to reason about that security model that we need to wrap around that. Virtual machines, as I mentioned, they virtualize or they emulate hardware. So they look and they smell like hardware. And you can define these simple hardware interfaces. We understand, after many, many years of deploying operating systems on hardware, what that looks like. It's much easier for us to reason about that security posture of a virtual machine as opposed to a container running on a shared kernel. What do I mean when I talk about isolation? I've mentioned isolation a couple of times now, so let's have a quick look at that. I took that photo, by the way. I'm a budding photographer. So first and foremost, what I mean by isolation, and when I think about that from a cloud provider's perspective, the most important thing for us is making sure we protect our customers. We protect our tenants from other tenants that are running in the same environment. And this can be protecting them from intentional malicious behavior, or it could be simply protecting them from noisy neighbors, an over usage of resources. We don't want a neighbor to interfere or impact the operations of another customer's application running. And we believe in this concept called defense at depth, and that is how we tackle all of our services. When we're building a service, when we're building a product, when we're building a project like Firecracker and the Firecracker-containerd project, we actually analyze each of those services using a framework called Stride. It's pretty well known, I think, in security circles. It's spoofing. It's an acronym. It stands for spoofing, tampering, repudiation, information disclosure, denial of service, and privilege escalation, or escalation of privileges, I think is the acronym there. So we look at all of our applications and services using that framework to try and make sure we thoroughly understand the potential attack vectors and security risks that may exist there. What we learn over time and what we understand to be the case is that the Linux kernel it's old. The primitives that exist within the Linux kernel aren't brand new, and they can be tweaked to improve isolation of processes that are running there. And a lot of the constructs that exist that I've just talked about help us solve those problems. But it still remains a single point of failure, if that's the right word to use there. And slight misconfigurations in the way that those features work and operate and interact can lead to potential threats in the space of privilege escalation or information disclosure. All of us in this room, I'm sure, have been using virtualization for some time now. Who's been using virtualization, by the way? Virtual machines, VMware? Yeah, as I thought, most people have been using it. So we understand how that works, as I said before. We understand and we can reason about the security models around virtualization. And at AWS, we've been using virtualization for a really long time, and we're generally happier not sharing a kernel between our workloads because we think it gives us a much stronger security posture when we start to deploy applications and our tenants and our customers start to deploy their applications. On the flip side of that, or should I say along the same lines of that, we can build the most secure system in the world, and obviously we try very hard to do that, but we also need to build a system that is usable. We need, I'm sure many people in this room have used cloud providers, and when we build these systems, we need to make sure that you can use them, and we want to make sure that you can bring your own tools to the party as well. And so things like Docker obviously is paramount to most of those conversations. Most people are familiar with Docker, and as Docker and general container utilization has evolved over time and matured, what we started to see is some standards emerge. Organizations like the CNCF that Scott was talking about earlier on play a big part in that, as does the Linux Foundation. Then we've got standards that are defined by the Linux Foundation, like the OCI, so the Open Container Initiative. And if we look at the Open Container Initiative, it defines a number of very interesting specifications, especially in the container space, around image standards. So it defines how the images that I referred to earlier on should be presented and represented and transferred to the location so that you can actually instantiate a container from that. And it also defines a standard for runtimes. So how do we actually run this container? How do we construct the environment that the container runs in? And how do we do that in a standard way, in an open way, so that we aren't necessarily locking anyone into using a particular type of container runtime or orchestrator? So things like the OCI are very important in that space. And when we're building any type of service, especially the ones I'm talking about today, we wanted to make sure that we had open interfaces or compatibility with those open specifications so that we could support other use cases. Whose phone was that? Okay, so what is a container runtime? Container runtime. So the standard Linux containers, and I'm going to go, most of my slides are questions, by the way, so I'm just self-questioning myself so I can ask them back to you. For standard container runtimes, Linux container runtime, this is the part that's responsible for actually assembling those Linux primitives. So when I create a container, when I use a kubelet or a virtual kubelet or I use Docker run, I'm using a container runtime of sorts to actually construct that Linux container for me, assemble all of the pieces to give me the environment in which my process can be isolated and can be executed. One of the standards that I alluded to earlier on, or mentioned earlier on, was the OCI standard for container runtimes, and that is actually largely based on the work that was done by Docker, and a lot of that was actually contributed to the Open Container Initiative from Docker. Those of you that have dived deep into Docker will be familiar with runc. Runc is a binary. Essentially, it's responsible for constructing the container as it runs on an operating system. And the runc represents essentially the reference implementation of the OCI specification for building a container runtime. Other runtimes do exist, and this is kind of what I'm here to talk about today, is one of the runtime implementations that we've developed for using a virtual machine, micro virtual machine service like Firecracker. I'll talk a bit more about that shortly. So containerd is probably the one that, and in fact, Scott had it up on the slide earlier on as well. Containerd is pretty much the standard reference implementation for a container runtime, or slightly higher order than the container runtime itself. But it's responsible for managing that life cycle of the containers as they run within your environment. It was, again, contributed to the CNCF by Docker, so it's a project that you can see by hopping along to the CNCF website now there. It's I can't remember the status of it, whether it's graduated or not yet, but it's definitely part of the CNCF, or was. One of the really interesting things for us at AWS when we were thinking about how we build this integration with Firecracker and containers and what runtime do we use, it was that containerd is written in a very, very modular way. Written in a way that you could integrate different types of capabilities. You could bring your own actual low-level runtimes. You could bring your own additional capabilities, so things like snapshotting, which I'll talk about very shortly, but it's very modular, so we can extend it and manipulate it and change it in ways that work for us without necessarily modifying the core capability of the functionality that it offers. So let's take a quick look at what containerd looks like under the covers. Sorry if anyone's already seen this diagram today or yesterday in any of the sessions, but I'll quickly walk you through what containerd looks like under the covers. Each of these blocks essentially represents the different modules that I mentioned earlier on. So at the top level there, we've got this gRPC API. So this is basically the standard way that we interact with containerd. From an AWS and a Firecracker perspective, what we're really interested in is the creation of the containers themselves and the bits that go into creating that container. So we're thinking about the file systems that are required to create the root file system for the container and how we mount those and attach those to a virtual machine within the context of Firecracker. So then we think about the content store. So the content store is a part of the containerd runtime, which is essentially responsible for storing all of that raw information that makes up your container's root file system. So when I have a container image and it's downloaded, inside of the tarball, or there is a tarball that essentially contains a representation of a root file system, and that tarball exists in its raw format within this content store. Then we've got this snapshotter component. This was one of the areas where we really had to start thinking creatively, and we'll see why very shortly. But essentially, the snapshotter is responsible for extracting or converting the contents of those tarballs that are stored in the content store into a file system that is compliant with the OCI standards and represents a file system that the container can actually use in order to run. It's at this layer here inside of the snapshot module that we implement things like the copy on write capability that gives us the optimized storage functionality. From an API perspective, each of the snapshots represents a full image to containerd. Now, the snapshotter itself, again, going back to the modularization of containerd, the logic that sits behind that can be anything. We can implement whatever we like underneath there, and that's where we really wanted to kind of inject ourselves and our own capabilities and experience to solve a few problems that we saw. So it does ship with some standard snapshotter functionalities in there, but then they come with different trade-offs like storage and space optimization used. And I'll talk a bit more about how we solved a snapshotting problem for our particular project. Then we've got the runtime piece at the bottom there. We click forward there. So this can basically use any OCI compliant runtime that exists out there today. It defaults to run C, which is the binary I mentioned earlier on. But it's plugin based again, so we can bring your own runtime, we can connect it in there, and this is where we wanted to look at bringing Firecracker into the equation. So I've talked about Firecracker a few times now. I'm sure you're all dying to know, if you do not know already, what is this Firecracker thing? So I'll take a few seconds just to quickly explain what Firecracker is and what its proposition is and why it helps solve some of the challenges that we were talking about a little bit earlier on. So it's a KVM-based virtual machine monitor. It's designed to run, instantiate, create micro virtual machines. Each of those micro virtual machines has a very limited device model and a very limited set of capabilities and functionality. And the reason we wanted to keep that device model and that functionality so limited was because it makes it much easier for us to secure that surface area, that vector. In addition to, so it's based on KVM, as I already alluded to. Hopefully the diagram gives you a good indication of where it sits in the stack. So we have our infrastructure there, which is our hardware. We've got our Linux kernel sitting there with the kernel virtual machine module sitting inside of that. And then Firecracker sits on top of that and uses those KVM constructs to actually build a micro virtual machine construct within which then we can essentially log in and run any kind of user level construct. But we need to be able to bring things like an operating system to the micro virtual machine. And we can do things like we do that using image files again, so we can bring uncompressed kernel image files that, as long as they're in an ELF compliant format, we can attach them to these micro virtual machines and actually boot this virtual machine and have it running and operational. We have this simple API. It's sitting at the front here. It's a RESTful API, and this is where we configure the micro virtual machine itself. So once we start the VM, or before we start the VM, we need to give it some instructions. We need to tell it what type of kernel to use, and we can essentially bring any kernel with a few restrictions around the fact that it can't be an uncompressed, can't be a compressed kernel image. And a few other little things. We can't use initial RAM file systems. I can share some more details later if you want to around that. But once we define the characteristics of the virtual machine through the API, we can then start the virtual machine using the API. And we get this very small, lightweight virtual machine within which then we can essentially run anything that is supported on the operating system that is running in there. I ran a session at the AWS Summit in Sydney a couple of months ago, which really went a bit deeper into Firecracker. I'm not going to do that today. today. But if you'd like to learn a bit more about Firecracker, hop along to the URL. It was a really cool session because I got to put some assembly code up on the screen and talk through how assembly code plays into virtualization and how we solved that challenge. So have a look at that. It's a kind of interesting video if I do say so myself. Okay, right, so now how do we go about creating how do we create micro VMs and then run containers inside of them, which is what we're really looking to try and solve today. We've got our micro virtual machine. Hopefully, again, by now, we start to understand why this hard shell around our existing container provides some additional benefits from a security and an isolation perspective. But how do we actually get those containers to run inside of these micro virtual machines? And that's the question that we asked ourselves when we set about building the containerd Firecracker integration. One of two main big diagrams I have for you today, just to walk you through what that process looks like. Again, some of the bits on here will look a bit familiar from the containerd diagram I showed earlier. We actually had to build about 4 new additional components for this project in order to fulfill or meet the purpose that we were trying to meet. So we built a snapshotter component, and I'll talk a bit more about that shortly. We built something we're calling the control plugin. We built a runtime, and then we built an agent component. Now, the snapshotter component is a block device-based snapshotter, and this will all become clear very shortly. It's essentially an out-of-process gRPC proxy plugin, which means that it doesn't have to be compiled into containerd, so it will run alongside the existing containerd binary without too much issue. Then we've got the control plugin, and the control plugin essentially represents an API, and we use this API to manage the life cycle of the virtual machine. So we interact with that API and we say, create me a virtual machine, configure this, attach some volumes over here. And we configure the properties such as the disk images that we want to use as well. Now, at the minute, and this is going to change, but at the minute that plugin, that control plugin, is actually compiled into to containerd. So if you wanted to use that particular, if you wanted to test this out today, you'd actually have to go and compile that in. It would be a special version of the containerd binary as opposed to just a plugin-based version. But we're working on that. And then we've got this proxy shim runtime component, which is essentially responsible for connecting containerd, which sits outside, into the virtual machine and the components running inside of the virtual machine. And inside of the virtual machine, when we have an agent. And the agent that runs inside of the virtual machine, you can think, and I'm going to use Scott's presentation from earlier to help kind of visualize this. It acts in the same way that the kubelet acts. So it runs inside of the virtual machine and essentially instructs the operating system how to construct the container inside of that virtual machine. The agent launches run C inside of that container, inside of that virtual machine. It's responsible for attaching the snapshots that we created using the snapshotter process earlier on. And essentially then what we have inside of that virtual machine is a container. It looks and smells and feels like a container. There's nothing different about it except it's a container running inside of a micro virtual machine running on top of another virtual machine. Turtles all the way down. So what is the block device snapshotter? So the reason we have snapshotters, as I mentioned earlier on, is that we use them to create these root file systems that we from the container images that exist today. Now, in the world of Firecracker and the containerd projects, when we download these container images, we're storing them on the host. We aren't storing them on the guest. So we need a way to expose those container images into the guest operating system that is running, because that's where our container runs. So we had to think through that because obviously for AWS and for every other cloud provider, as far as I'm aware, security is job zero and the most important thing we do. And we couldn't figure out a secure way to share files between environments, between the guest and the the guest and the host. So what we ended up doing is we ended up implementing a block device snapshotter. So the way we do that essentially is we take the image that we download from the content store, we suck that image in, we unpack the tarball, and we actually create a block device, and we write the entire contents of that tarball to a block device. That block device exists on the host, and then we use that block device and we mount that block device to the Firecracker virtual machine. And then once the block device is presented within the Firecracker virtual machine itself, the agent is able to pick up that block device and mount it to the container that is running inside, and then we get our root file system for our container in there. We actually wrote two different types of block device snapshotter. One of them we call a naive snapshotter, and it was something that was really written for more of a proof of concept, and essentially it did pre-copying. So every time we created an image, it created a new copy, and if we added anything to that image, it would need to create another copy of that image. So very inefficient in terms of the storage space that it would use, but it helped us prove a few points. We then evolved over to use this device mapper based snapshotting functionality, and device mapper is a Linux framework for essentially mapping physical devices to virtual devices. So we use a device mapper to build these block devices, represent these block devices to our virtual machines. And because we're using the device mapping functionality, we're able to gain some benefits from a storage utilization perspective. The device mapper uses thin provision pools of storage, represents them as devices, and we can share then blocks across multiple different types of containers. So we get the benefits of deduplication in that particular scenario there. We've recently merged this into upstream containerd, so I've dropped a URL at the bottom there if you want to go and look at the pull request and read through some of the banter that was having backwards and forwards around that pull request. It's quite interesting. So that was the snapshotter. Then we've got where am I looking at time here? Then we've got the control plugin. So the control plugin is essentially responsible for the VM-specific settings. So we're using this control plugin to direct what the virtual machine should look like. Create me a virtual machine with these properties. I want to have these devices connected to it. I want to have this much CPU and this much memory. Now, as I mentioned, this is compiled into containerd. The reason it's compiled into containerd at the minute and not a dynamic plugin is because we wanted to be able to expose the API that this presents using the existing containerd API socket, as opposed to having it exposed over a different socket. That would cause a few challenges downstream with a few other clients that needed to connect and interact with that service. In the future, we may look to move this out, and we'll tackle that problem as we go through the evolution of the project. And then we've got the runtime. So the runtime is responsible for sitting outside of the virtual machine, interfacing with the control plugin, and it's responsible for proxying instructions into the virtual machine itself. It talks to the agent within the virtual machine using a construct called VSOC. We have each of the virtual machines has a VSOC socket, and we pass instructions into the virtual machine via this VSOC socket. We're implementing this using the containerd v2 API, not the OCI specification. There's a few reasons for that, and I won't dive too deeply into that because I'm very conscious of time. But it provided essentially a little bit more flexibility to us from a process invocation perspective. What about the agent? So I mentioned the agent in my diagram a little bit earlier on as well. Now, the agent is the bit that sits inside of my virtual machine, akin to the kubelet that Scott was talking about earlier on. And it sits inside of that virtual machine and is responsible for invoking runc for me. So it's going to call runc, and it's going to tell runc to create me my containerized environment using all of the primitives that I talked about during the beginning of the slide here. So it's going to trigger the construction of things like namespaces and C groups, which the container itself will actually run in. And the reason we want to continue to use runc, we haven't done anything too differently yet, is that we wanted these to look and feel and smell like containers that we all know and love today. See earlier slide about building a seamless experience for our customers who want to use the same types of tools and workflows that they're already using today. So when you create this virtual machine inside, the container inside of the virtual machine, it will look and feel and smell essentially like a container that you're used to running on your own laptop if you have Docker for Mac installed. Yeah, so wait, what? So I've tried to diagram this a little bit to help make it a bit clearer, and understand this may not necessarily be the clearest of diagrams as well, so sorry about the eye chart there, but this kind of gives you an idea of the workflow that we're going through here when we actually instantiate a Firecracker virtual machine and we run a container inside of it. So we have an orchestrator, X. It invokes containerd or calls containerd. It's passing talking to containerd is downloading an image. It's passing that to the snapshotter. The snapshotter is unpacking that image, writing it to a block device. The runtime at this point in time is also talking to Firecracker. My apologies, sorry, the control plugin is talking to Firecracker and saying, go and create me a virtual machine that looks like X. Whilst all of this is happening, Firecracker is building my virtual machine for me then. The runtime then is taking the disk images or the block devices that have been created by the snapshotter, and it's presenting them to the Firecracker virtual machine that's now been created. Inside of that then, the agent itself, once the Firecracker virtual machine has started up and the kernel is loaded, the agent's then looking for those devices that are attached to the virtual machine, and it's using them alongside the runc binary that it's invoking to actually build the container, mount the block devices, which essentially represent the root file system and the kernel image, and lo and behold, see previous slide with the magic, we have a container running inside of a virtual machine in much the same way that your container would run in any other environment, with the exception of having a nice hard virtual machine shell sitting around the outside of it. So what is the current status of the project so far? Everything is prototype right now, but it does work. I don't have a video to show you today, but it does work. And I would say if you want to have a play with this, please go along and have a look at the project, the GitHub page, which I'll show you very shortly. We're working on a few optimizations with regards to the communication between the runtime and the agents. That is because the implementation, the VSOC implementation that we're currently using is an experimental implementation at the minute. So we have a few things to tweak and change and manipulate around that as VSOC itself matures. We've also got a few challenges that we're trying to address around mapping of block devices to Firecracker itself, the Firecracker virtual machines. At the minute, because of the complexity of the device model and the functionality that we wanted to reduce on Firecracker virtual machines, we don't really have a way to dynamically attach storage volumes or block devices to those virtual machines. So we have to pre-allocate those block devices to those virtual machines so that they already exist, so that we can then redirect them to the block devices that we create through the snapshotter process. All in all, though, these enhancements that we're making are leading us to a point where we'll start to be able to run multiple containers inside of a single virtual machine. And obviously, that then opens the door to constructs like a pod or a task if you're thinking about Amazon's Elastic Container Service. So multiple containers, and again, also we want to afford the ability for users of this to be able to run commands like docker exec, so that we can execute and run components inside of these micro virtual machines in the same way that you would do if you were running it on your own virtual machine. So the project is open source. I would encourage you to go and have a look at the URL there if you're interested in learning a bit more about it. The top level of that URL is the kind of core project for Firecracker itself. The sub-project you've got there is the firecracker-containerd integration that we've built. We'd love to get your feedback. I'm conscious that I'm chewing almost into lunchtime now, so I won't take any questions now. But what I will do is I'm going to be here for the rest of the day. So if you'd like to come and talk to me about this or any of the other work that we're doing over at AWS with regards to containers, I'd be happy to chat with you. I've also got my colleague Jason Umika over there as well, so he's here to chat as well if you'd like to have a chat about anything. But thank you very much for your time. Sorry I overran by a few minutes.